So let's talk about the contrast sensitivity and what is meant by contrast. So contrast is the degree of blackness between black and white. So how much the black is black and how much the white is white. And what is the difference? What this is the contrast. So if I'm talking about the threshold and sensitivity, so threshold is the reverse of sensitivity. Threshold meaning that the smallest amount of difference in the contrast that can be detected, or the smallest amount of contrast required to be able to see the target, while so the smallest will be the highest sensitivity, as it is the reciprocal of the contrast threshold. So if I have high contrast sensitivity, this means that the threshold for seeing the contrast is very small. So if we can see this is you can see that the colors are in the shades of gray. If we can see the word here with a little difference between the word and the background, then this is called the higher sensitivity of contrast. But if we cannot see and we can see only the white word in the background, black background, this means that we have low threshold or high threshold or low sensitivity. So we just mentioned about that we have already a test in the clinic called the Snellen visual acuity. So why we do need a test for the contrast sensitivity? Does the Snellen visual acuity is can make us do without the contrast sensitivity? So the answer is no, because the Snellen visual acuity chart is tested against very high contrast sensitivity or very high contrast. You have the very white background and we have very black optotypes, so that if the patient has impaired contrast sensitivity, you will not be able to detect it because they may have a good Snellen visual acuity, but still they are visually handicapped in real life situations because they have poor contrast sensitivity. So the visual actually drops in the situations with low contrast and the quality of the vision is not good. And this information or the contrast is not obtained from the visual acuity chart. So the contrast sensitivity is usually a better predictor for the visual performance than the visual acuity. The contrast sensitivity can be measured in different forms. So we have different components here. The first one is the degree of blackness and whiteness of these stripes. So as you can see here, this is of low contrast and this is of high contrast, and there is high difference or large difference between the black and white here, but this difference is decreasing as we get here. There is another term or another measurement in the contrast is called the grating acuity. Grating means that the width of the white and the black bands. So how much they are white? Is it higher grating or lower grating? So it will be the width of the alternating dark and white bands. We have mentioned about the Vernier acuity. It can be also considered, or it is this is different from the contrast sensitivity, as we can see only how can we detect a break in a line. So this is different. Also, there is another measure in the contrast sensitivity is the time. So this alternating bands or this dark and white bands can change during the time, and this can be another measure in contrast sensitivity. There is a curve that will represent the contrast sensitivity. It is called the contrast sensitivity function. The contrast sensitivity will depend on the spatial frequency. Spatial frequency meaning that it is the frequency of the alternating dark and white bands. Is it too many so that this is high spatial frequency, or if they are too few, so this is a low spatial frequency. So the ability to detect the or the contrast will depend on how much the alternating dark and white bands repeat and how much they are close to each other. So the special frequency of the visual stimuli is given by cycles per degree. So in order to measure this alternating dark and white bands, this can be considered in cycles per degree. So how much cycle per 1 degree? So you can see that there are many cycles. Here are less cycles. So this is considered a higher special frequency. The contrast sensitivity function is a subjective measurement of the person's ability to detect a low contrast pattern stimuli, usually using vertical stripes of decreasing shades of black to gray. Thus, the resulting measurement is said to give more accurate representation of the eye visual performance, meaning that in order to represent or to measure the patient contrast sensitivity function, we represent black and white stripes. These black and white stripes become narrower, so and they become more gray. So this black becomes more gray, and we measure the patient's ability to see them. So here is the contrast sensitivity function increasing by 0.1 to 0.2, 0.3, 0.5, and here is the special frequency by cycles per degree. As you can notice, as we increase the cycles per degree, the contrast sensitivity function will increase up to a limit. So the maximum contrast sensitivity will be at 10 cycles per degree. This is the maximum or the peak value for the contrast sensitivity function. As the frequency gets higher, you can see that there is a decline in the contrast sensitivity function, as you can see here, so that because there is higher special frequency and there is a limitation of the photoreceptor that they cannot see this higher special frequency. Again, this is the contrast sensitivity function curve in which the patient can see this is the visible, or this is what can if there's the threshold. This is what the patient can see. Above this curve, the patient cannot see or invisible. And this is the special frequency by cycles, and the maximum will be at about 10 cycles. And this, after this, the curve will decline as the threshold here will decrease and the sensitivity will increase. So this is the sensitivity and this is the threshold, both the reverse. So as the contrast sensitivity increase, the threshold decrease and the sensitivity increase, but till a certain limit when the special frequency become 10 cycles per minute or per degree, then the contrast sensitivity starts to decrease and the threshold will increase. So the contrast sensitivity is presented as a curve which plots the lowest contrast level a patient can detect for a specific size target. The x-axis here curve is for the special frequency, while y-axis is for the contrast sensitivity. So here is the curve when we are presenting to the patient gratings of low special frequency, of low cycles per degree. The patient can be able to see them, and the contrast even increased when we increased the frequency, but up to a limit like about 10. As we increase the frequency furthermore, the contrast sensitivity is decreasing. So what are the functions, or what are the components of the contrast sensitivity charts that we measure? As we mentioned, we first measure the gratings. So the gratings can be a measure for the contrast sensitivity by presenting the patient alternating dark and white bands. So each adjacent or one adjacent pair of dark and white band, this can be make up a one cycle. And as the thickness of these bands increase, this means that this is a low special frequency. If the bands or the thickness of these bands increase, this is considered a high special frequency. The gratings can be represented in another form called the sine wave or sinusoidal. In the sinusoidal, there is no sharp border between the alternating dark and white bands. You can see that there is no sharp border. These bars are not distinct, but they are wavy, and they are mixed together, so they are don't have sharp border. And these are sometimes can be used in some tests because they have some advantage that if the patient has some high order aberrations like spherical aberrations or chroma aberration or chromatic aberration, or they have diffraction or light scatter, these type of test or these type of gratings is not affected by the aberrations or not affected by these errors in the optical system. So when we measure it, this is a true representation of the contrast, and the special frequency are represented here. This is in contrast to the square wave gratings. So in the square wave gratings are like squares alternating dark and white squares that have sharp edges. So this is different from the sinusoidal. So what are the types of contrast sensitivity? We have two main types. We have the spatial contrast sensitivity and the temporal contrast sensitivity. And temporal here is not related to the temple, but related to the time. So temporal is measuring of the contrast sensitivity in relation to the time. So the spatial frequency is the type that we have just been mentioning, which is detection of the striped pattern at various level of contrast and the spatial frequency. So we increase the width and or decrease the width of the spatial frequency. We increase and decrease the degree of whiteness or blackness of the stripes. So that's what's called the spatial contrast sensitivity, in which we present a patient sine waves or sine wave gratings of parallel light and dark bands and measured with a stationary grating. So you just present the patient a grating or a chart with grating that have stationary. So you can like this. So alternating dark and white bands, then they disappear and another one appear, or they can be or they are close to each other or in the same chart, and ask the patient what is the minimum contrast sensitivity or the minimum the highest sensitivity or the minimum threshold that he can detect. So the width of the bar can be a representation of the spatial frequency. So if we make these bars are very narrow, this patient has a higher frequency or higher spatial frequency, and this will be indicative of a higher contrast sensitivity. If these bars are wide, then this will be representing of low contrast sensitivity and low spatial frequency. If we do this to a patient, the spatial frequency increase from the left to right and by logarithmically from 100% at the bottom to about 0.5 at the top. So at the bottom, we increase the contrast sensitivity, or at the bottom, the spatial frequency is increasing from the left to the right, so that from in the left, the bars are wide, while at the right, the bars are narrow. So the spatial frequency increase from the left to right. Also, the contrast increase from below to above. So below it will be 100 here. As we go to the top, it will be about 0.5. So below you can differentiate between black and white, while above you cannot differentiate between black and white. So is this pattern remind you of anything? Does it remind you of a specific curve, or what's called the contrast sensitivity curve? So here is what the patient can see exactly. The patient can see this is the contrast sensitivity function. So as we increase the spatial frequency from the left to right, and we increase decrease the contrast from below to up or decrease the contrast from below to above, then the contrast or the threshold of the patient or the sensitivity, let's talk about the sensitivity. The sensitivity increase as we go up above until about 10 cycles, or the spatial frequency of 10 cycles per degree or per minute. or per millimeter on the retina. Here the curve start to decline and you will be not be able to see above this curve, but we can see only below this curve as you can see here. So this can be seen and this cannot be seen. So this is called the special frequency contrast sensitivity. The other type of the contrast sensitivity is called the temporal contrast sensitivity, in which the gratings reverse contrast at various rate of time. Let's say, for example, that this is the alternating dark and white bands, and you can see the same circle will later on, by as time goes by, these bands will decrease in width and will decrease in the contrast sensitivity, so they become more gray and they become more narrow until the patient is not able to see them. So this can be a measure against the time. So both systems, either the special frequency contrast sensitivity and the temporal one, both of them can give a more complete information about the visual performance. There are neural mechanism of the contrast sensitivity that is not well understood, but for the on the brain level, but on the retinal level, it is this contrast sensitivity is not uniform because the retina itself is not uniform. So the fovea or the posterior pole is responsible for the higher frequency or higher spatial frequency. This can be detected by the fovea, while the retinal periphery will only see the lower frequency, not the high frequencies. This is because the retina itself have different types of cells that will be discussed in the retina lectures, but we just mentioned about them in the anatomy of the neural pathway. So we said that the ganglion cells are divided into P cells and M cells. The P cells are these cells present in the retina will synapse at the parvocellular layer of the lateral geniculate body, and the M cells in the retina will synapse at the magnocellular layer of the lateral geniculate body. The difference between the P cells and the M cells is that the P cells will show small and slowly conducting axons, and this will have higher spatial resolution. So the P cells will show higher spatial resolution. The M cells will show large and fast conducting axon that will perceive large areas of the visual field, so they will show higher contrast sensitivity and temporal resolution, but lower spatial resolution. Again, the P cells will show higher spatial resolution when they receive stimuli of higher spatial resolution, while the M cells receive stimuli of lower spatial resolution, but higher contrast sensitivity and higher temporal resolution. The patient who have impaired contrast sensitivity will have problems with night driving and problems with seeing the light. They may be exhausted during reading as his eyes become tired, also during watching television. So this is the patient who have normal vision, and this is a patient who have poor contrast sensitivity. So everything, the definition between the colors is impaired. To measure the contrast sensitivity, as we mentioned, we have two variables: the degree of blackness in relation to the white background and the distance between the grating per cycle per degree of the visual angle. There are different tests to measure the contrast sensitivity. Let's review the most important ones of these tests. There is a famous chart called the Pilley-Robson chart. The Pilley-Robson contrast chart, they presented two bars of letters. Each bar will consist of 3 letters. Each bar will or each 3 letters will have different contrast sensitivity than the letters below. So we ask the patient which letter that he can see clearly at 1 meter distance and until the last line that the patient can see clearly. As you can see here, this is the Pilley-Robson, And so you can see H and S and Z and R. So you can see this, okay, then R and C and K and O. So we cannot see these, the remaining lines. Okay, this is the 1.5. This is his contrast sensitivity. The other test is called the Cambridge Low Contrast Grating. This is the screening for the contrast sensitivity made at about 6 meters, or the patient is tested from 6 meters, consists of 12 pairs of plates, consist of stripes of variable contrast. The first one is for demonstration and the others for testing. So you are presenting these stripes. The patient is asking, okay, this is alternating dark and white bands. They are vertical, in the vertical direction. So they are then present different plates of decreasing contrast sensitivity, as you can see here, until the last plate that the patient can see clearly. The Belly-Love chart, we said that it is a visual acuity chart, but it can be used also to measure the contrast sensitivity. So not only the visual acuity, but it also can be used for the contrast sensitivity. So how can we do so? It is just by decreasing the degree of blackness of the letters. So instead of use of 100 contrasted chart, we decrease the contrast like about 10%, 20%, 30%, 90%. So this can be a measure for contrast sensitivity. Another test called the FACT, or the Functional Acuity Contrast Testing, that consists of a chart with sine wave gratings of variable frequencies, and the chart will test the 5 special frequencies and the 9 level of contrast. So 5 special frequencies or 5 sizes of the gratings and 9 levels of contrast, 9 grades of difference between black and white, as you can see here. So this is the 9 plates and 5 special frequencies. So as we go from A to B and to C and D, there is increase in the special frequency. As we go from 1 to 9, there is a decreasing in the contrast sensitivity. So until we reach what is the letter or the box that the patient can see, like 5C or 6C or 7D. So this is called the Functional Acuity Contrast Test. Another test is called the Arden Plates Test, which consists of a booklet, have 9 sine wave gratings, and they are oriented vertically, and this the contrast will variable from the top to bottom, and so you can see that the sine waves itself have different special frequency, and also they will have difference in the contrast sensitivity. The Weisstedt contrast sensitivity test, it is another test for the contrast sensitivity, depends on the sine wave gratings. They will have 5 rows and 9 columns of circular photographic plates or discs on a gray background. They have different special frequencies, so this will be the same principle again and again, presenting the patient different plates of increasing special frequency and decreasing contrast sensitivity, and ask the patient which letter he can see clearly. You don't need to memorize all details about these tests, but this is just to know what test is or what is the function of each test. So in the exam, you will be asked what will be the function of the Pelly-Robson chart. So you should know that it is for contrast sensitivity, but usually the fine details are not asked in the exams. Finally, what are the factors that will affect the contrast sensitivity? We have again extrinsic factors. This will be the same like the luminance again will control. The more the luminance, the better the contrast sensitivity. The target size, so if it is large enough, it will cause better contrast sensitivity. Grating motion, if it is fast, then it will be different to or difficult to differentiate between the white and the dark bands. Grating shape, if it is a square, it will be easy, it will be better contrast sensitivity. If it is sinusoidal, it will be poor or will give a poor performance in the contrast sensitivity. And we have different intrinsic factors. Let's review them. Refractive error. So if the patient has a refractive error which is uncorrected, this will lead to decrease in the contrast sensitivity. We will start first by the smaller grating size. or the higher spatial frequency for mild refractive error. So, but if it is increasing, then the contrast sensitivity declines, and the middle and the larger grating sizes, so the patient cannot see the middle or large gratings, or which have low spatial frequency, and also the patient will the patient will have a poor contrast sensitivity. The age, as the visual acuity decrease with age, there will be decrease in the contrast sensitivity with age. Maybe due to spherical aberrations of the lens. It was thought that the spherical aberrations that occur at the crystalline lens level will contribute more to decrease the contrast sensitivity more than even the cornea. So the young lens will focus the light on the retina, but there is a spherical aberrations occur at the aging lens, so that it will not focus the light on the cornea, causing a poor visual performance. And this will be the effect of the crystalline lens more than the cornea, causing poor, although the patient may have a 20/20 vision or 6/6 vision, but they will have a poor contrast sensitivity. Cataract is one of the main reasons for decreasing the contrast sensitivity, and even before the affection of the visual acuity. So the cataract can cause a contrast sensitivity loss, usually similar to the refractive error at higher spatial frequency. So as the refractive error causes initially a loss of the higher spatial frequency, the cataract will do as well. But the cataract can cause the glare, or can cause glare, so that the glare will exacerbate the poor contrast sensitivity. So especially for patients who have posterior subcapsular cataract, or they have the patients complaining from cataract, these patients will complain of visual symptoms like glare and halos. These visual symptoms will even contribute more to decreasing the contrast sensitivity. The contact lenses, if they are poor fitted, then this will cause a residual astigmatism, or if there is a residual astigmatism in the contact lens, this will cause a refractive error that will lead to decreased contrast sensitivity at the middle and the higher spatial frequency when compared to the hard contact lens. Diabetic retinopathy can also decrease contrast sensitivity of all grating sizes. And optic neuropathies also can cause decrease of the contrast sensitivity. One of the main or one of the findings of the optic neuritis treatment trial that the contrast sensitivity is the first function of the optic nerve to be lost. So in optic neuritis, or especially or retrobulbar optic neuritis, they can cause different affection or different manifestations like relative afferent pupillary defect, decreased visual acuity, but the contrast sensitivity will be affected the more, and will be affected for some or more or all grating sizes. Pituitary adenoma can also cause a contrast sensitivity loss at the middle grating sizes. Toxic chemicals can do this as well, can cause affection of the contrast sensitivity, especially for workers working in working in factories and exposed to some toxic materials. And we all know that the contrast sensitivity is affected by the LASIK. So the LASIK will cause cutting of the optic of the long ciliary nerves due to creation of the flap, and these nerves are essential for sensation and essential for the contrast sensitivity. So although the patient can see 20/20, but they may be bothered by the poor or decreasing the contrast sensitivity.